Welcome back to Control System Lectures. In this video, I want to introduce a topic that is sort of a bridge to larger and more useful discussions on system stability. Before we jump right into them, I think it's important to set the stage first and describe why we need so many different types of design tools in classical control theory. And maybe in the process, we'll answer a few lingering questions you might have about them. Some of these topics include the Routh-Hurwitz criterion, Nyquist plots, Bode plots, and root locus. Therefore, in this video, I'm just going to address really the following question. How can we determine the stability of a closed-loop control system? And by answering that question, we'll be ready to move on to what are extremely powerful tools in control system design and analysis. Before we march off and start answering that question directly, I want to make sure we're all on the same page regarding some terms. Namely, some interesting differences between open-loop and closed-loop control systems. If you've never heard of these terms, I recommend that you first check out my video on open-loop and closed-loop systems. But if you have a general idea of what they are, then the next section might provide a little more understanding. By definition, open-loop control systems do not use feedback to determine if the system has met its desired state. That is, they don't observe or sense the output. A block diagram of an open-loop system might look something like this. The input into the system is the reference signal, or the commanded state, and the output is the observed state. By contrast, a closed-loop system does use feedback of the output state to alter the input. However, as you can see, the original reference signal is now the output of the comparator, and the new closed-loop reference is a completely new signal. What I find interesting about this is that the difference between open loop and closed loop is dependent on what you label as the reference signal and what is the output. I could take everything inside of this dashed box and call it the plant. And now, since the reference doesn't depend on the output of this plant, it can be considered an open loop system again. Let me give you an example to illustrate what I mean. Say you were given a rock that was sitting on a table, and you were told to keep that rock exactly at the same spot on the table, even in the presence of disturbances, like the table is shaking or really high winds. You want to model the system, so you start with the transfer function, where the input is force, and the output is the position of the rock, x. Now you could either look this up in a table, or you could easily calculate it to be 1 over ms squared. And you can draw the block diagram like this. And what this is saying is that if you apply a force to the rock, it's going to start to move. And you can see that this transfer function makes sense, since if you have a force input, you can divide by mass to get acceleration. And when you integrate acceleration twice, you get position. And since 1 over s is the Laplace transform of an integral, that's exactly what the transfer function is doing, to transfer the force input into a position output. And this is an open loop system because the amount of force needed to keep the rock exactly at the same spot is not dependent on where the rock is currently located. If a disturbance force moved the rock, without knowing where the rock was, you wouldn't know how much force or in which direction to apply it. As a side note here, you could attempt to measure the disturbance force and counter it with an equal and opposite input force. But the system would still be subjected to disturbances that you don't measure or didn't know about, and any error in the measurement will ultimately add error to your result. At this point, you decide that in order to meet the requirements, you have to add feedback to adjust the amount of force on the rock based on its position. To do this, you attach the rock to one side of a spring, and on the other side of a spring, you put a solid wall. Now, the spring produces an additional force that is negatively proportional to its stretched distance. Or writing this in block diagram form, we can feed back the distance, multiply it by spring constant k, and subtract this force from the reference force. Now, if there's a disturbance on the system, the feedback path will cause the system to oscillate around the initial starting position. Feedback is definitely an improvement, since the rock will always tend to oscillate back towards the reference position. But it's probably not good enough, because without any damping, the rock will continue to oscillate forever and never actually come back to rest at its reference point. But let's look at this. We have this closed loop system. But if we treat the spring and mass together as the entire plant, we can rewrite the transfer function in this manner. 1 divided by ms squared plus k. And now this looks like an open loop system. Or more specifically, we're treating the feedback path as the plant and it's accounted for in the transfer function. But mathematically, there's no difference between this transfer function and the system just above it. Now when you add disturbance, that internal feedback path is going to cause the rock to oscillate around its reference point. Now with this transfer function, we can add another feedback path, say a damper to damp the oscillations over time. And just like we did before, we can condense this block diagram into another single open loop transfer function. So you can see when you add feedback control to an open loop system, you are changing the dynamics of the system, generally making them more complicated. However, once you rewrite the dynamics in the familiar open loop way, then the same analysis techniques will work for both. So the question becomes, how do we determine the stability of this open loop system? And then, by rewriting a closed loop system, can we just apply the exact same techniques to both? All transfer functions can be rewritten as the division of two polynomials, a numerator and a denominator. We determine stability of an open loop system by looking at the poles of the transfer function, which are the roots of the characteristic equation. These roots will have a real component and an imaginary component. For this example, this transfer function g of s has roots at -1 and -2. Now you can plot these roots to see them visually or just assess the stability directly. If all of the roots exist in the left half plane, that is that they have negative real components, then the system is stable. This is easy to prove using the inverse Laplace transform of g of s. You can simplify the transfer function using partial fraction expansion. And what you'll be left with is a summation of poles with various gains, a and b in this case. Now taking the inverse Laplace is the gain of the numerator times e to the st. And if each s, or each root, is negative, then the response will decay exponentially as time increases, which is a stable system. So if that's how we determine stability of an open loop system, your next question might be, how is that any different than what we would do for a closed loop system? So your first guess for determining the stability of a closed loop system might be 1. Rewrite the system as an open loop transfer function. That is, basically reduce the block diagram into a single transfer function. 2. Solve for the roots of the characteristic equation. And then the third step would be to look at the real component of those roots and determine whether the system is stable or not. That seems easy enough, right? Well, let's try it in practice. Let's take an open loop system that has two separate processes, a control process H and a plant G. And this is an open loop system, and so we know that we can determine stability by looking at the poles of the combined transfer function H times G. But what if we close the loop? We can rewrite the transfer function as h times g divided by 1 plus h times g. And this is a closed loop system. But stability is still found by looking at the open loop representation. So in this case, it's by finding the roots of 1 plus hg. So it looks like all you have to do is add 1 to the open loop transfer function and then solve for the roots. Great. So why don't we do this all the time? Why are we bothering to use tools like Bode plots or Ralph Hurwitz criterion or Nyquist plots or the root locus method? Well, the answer has two parts. The first part is that with the advent of computers and software packages like MATLAB, solving for these roots are no problem. However, historically, solving for these roots was a huge problem. Try solving for the roots of an 8th order polynomial and see how easy it is without a computer. People were able to determine the roots of g times h, though, because both the controller and the system dynamics are built up with poles and zeros such that the roots are easy to see. This usually falls out that way because of the way that the dynamics are modeled and because the control system is chosen by the engineer. You can see very easily in this example that the roots are at -1, -3, -4, and 0. And you know that this is a stable system. But once you add 1 to it, factoring this mess and trying to find the new roots becomes a huge problem. Not only that, but the second part of this answer is that even though the plant is usually fixed, the controller H is changing to meet design criteria. So when you're trying to design and tune your controller, you're left with this problem. How do I change my controller H so that 1 plus Hg is a stable system? And not just stable, but that it also meets all of the desired stability margin and performance that is required. And this is exactly why we have several different design and plotting techniques available to us. These methods were developed years before the computer was invented in order to allow a controls engineer to design and tune a controller. That is basically just determining the roots of 1 plus Hg. And even though we have computers that can help us with this task today, fully understanding these methods is vital to making you a good controls engineer. As I said at the beginning, this video is just to whet your appetite and get you excited to learn about these techniques. Over the next few videos, I'll go into depth about 4 very popular methods for determining closed-loop stability and design. These are the Routh-Hurwitz criterion, the Nyquist plot, the root-locus, and Bode plots. And I'll explain how we use each of them to design, tune, and ultimately understand our control systems. If you don't want to miss any of these future lectures, don't forget to subscribe to my channel. Also, as always, please leave any comments or questions that you have in the space below, and I'll do my best to try to get back to you on them. Thanks for watching. I'll see you next week.